All right, good morning, good afternoon, good evening, class. Today in chemistry, we're going to talk about Le Chatelier's principle. So the last couple of days, we've been talking about equilibrium, and yesterday we discussed spontaneity in reactions, and then we discussed uh, where or how a reaction gets to either equilibrium or gets to spontaneous states based on entropy and enthalpy, whichever side of the reaction is favored by entropy or enthalpy. All right, today we're going to talk about something that kind of relates to that, and it uh, applies entirely to systems at equilibrium. And this is Le Chatelier's principle. And it's really neat because we use this a lot in chemistry to manipulate chemical reactions. Because, well, we'll talk about it. So, Le Chatelier's principle can be summed up as follows. Okay? And Le Chatelier, for background information, was a French chemist who studied equilibrium. He noticed that in a closed system, if that's in equilibrium, is subjected to some kind of change, then the chemical system is going to want to do things to undo that change. Okay, so I'll repeat that again. So if a closed system is in equilibrium and then we do something to change it, processes inside that chemical reaction will occur that will counteract that change. Okay? It's a neat concept. What this allows us to do is it allows us to predict what will happen when conditions change in a particular reaction. Okay? So this is all part of systems wanting to go towards a state of equilibrium because they're happy. They're happy at equilibrium. Okay? So when you change something about the equilibrium, then the system will want to reestablish a new equilibrium, okay, based on whatever change you did. It tries to undo that change. Okay? All right. So there's a couple of things that you can do to affect the equilibrium of a system. The first is change the temperature. Okay, so let's consider the following. This reaction is an exothermic reaction. Okay, bring it up. So this is nitrogen monoxide plus some chlorine gas will produce NOCl. So this reaction is an exothermic reaction. We can tell it's exothermic because it is releasing energy. So it's an exothermic reaction that gives off energy. Okay. Now, if I were to change the temperature of this reaction, so for example, let's say I were to raise the temperature. So let's raise the temperature. Okay. The change that you would see in this reaction is the amount of energy in the system goes up. So if raised temperature equates to a more energy in the system. Okay, now let's just tell you this principle. If this is closed and we suddenly add more energy to it, the system will want to get rid of that energy. So the system will use up extra energy. Okay. Now, what does this mean with this reaction? Well, remember, this reaction is in equilibrium. So we have an equal amount of forward reactions and an equal amount of reverse reactions. So if the system wants to use up the extra energy, then it means that the reverse reaction will occur slightly more often because it wants to use up the extra energy in the system. In order to do that, it has to go backwards. Why do we know it goes backwards? Well, the reverse reaction is endothermic. We already identified that the forward reaction is exothermic because it's producing this energy. So that means then that the reverse reaction must be endothermic. So the reverse reaction increases. So when the system uses up the extra energy, therefore the reverse reaction occurs faster or more often. Oh, whoops. reverse reaction occurs more often. I don't know what I was writing. Occurs more often. Okay, and then the equilibrium shifts to reactant side. Okay. Another way of phrasing this is the equilibrium will favor the reverse reaction, or the equilibrium will favor the so equilibrium will favor the reverse reaction, or equilibrium will favor the reactants. Okay. Now, let's suppose that instead of raising the temperature, we lower the temperature of the reaction chamber. So if you lower the temperature, what this does is it lowers energy. So lower temperature means less energy. Okay, less energy in the system. Now, the system will want to counteract that smaller amount of energy by creating more energy. So the system wants to create more energy. System wants to create more energy. And how can I do that? Well, looking at my reaction, well, at the beginning we said the forward reaction increases or is exothermic, so the easiest way for the system to create more energy is to run the forward reaction more. So in the effort to counteract what you've changed, the system runs the forward reaction more often. So forward reaction occurs more often. And this is effectively the same as saying that the products are favored. Or equilibrium shifts to the products. That's probably the better way to put it. That's what I said last time. So equilibrium. So the equilibrium shifts to products. Okay. Or another way of saying this is that the forward reaction is favored. Okay. So if the forward reaction is favored, the equilibrium shifts to the products. Okay. Now, every reaction will, this is true for an exothermic reaction. For an endothermic reaction, the opposite is true. If you lower the temperature in an endothermic reaction, the reverse is going to happen more often because that's how the system creates more energies, by running an endothermic reaction in reverse. Okay. So when looking at a temperature change, be mindful of where the energy is. If you lower the temperature, the reaction will want to create more energy. So in this case, the energy is here in the product side. If you lower the temperature, it'll move towards the products. If the energy were on the other side, like here, then if you lower the temperature, it'll move the other way. And then the opposite is true for if you were to raise the temperature. Okay. All right. Now, a second way we can manipulate this reaction is by changing the concentration once the system has reached equilibrium. So we'll use the same reaction. And I'll highlight this. Well, I'll talk about one, maybe two of the things we could change. There are three things we could change. There's the NO, the Cl2, and then the NOCl. So once the system is in equilibrium, we can change these concentrations. Okay. So for example, let's add some NOCl to this, and what reaction rate would increase? Would it be the forward reaction or the reverse reaction? Well, let's think about it. If we add more NOCl, so that'll be there, more NOCl, we're doing sort of two things. One, simply we just have more NOCl, so the chance of NOCl molecules colliding is increased. Okay, so by increasing the amount of collisions of NOCl, then we effectively cause the reverse reaction to occur more often. Okay, so NOCl can collide more often. Okay, and therefore reverse reaction is favored. Reverse is favored. Okay, there we go. So the reverse reaction is favored simply because we have more NOCl in the reaction chamber. They can collide more often, and therefore the reverse reaction is favored. a way to think about it is, okay, if I increase this amount, then I'm going to drive the reaction this way. Okay. Now, suppose we were then to, rather than increase the amount of NOCl, instead we increase, what if we increase, instead of NOCl, what if we increase the amount of NO? Well, we can think about it the same way. If we have more NO, that means that more NO can collide with chlorine, which means my reaction is going to be driven this way. So in this case, the forward reaction is favored. Wait, did I say reverse reaction prior to that? Oh no, I think I got it right. I got it right. All right, so yeah, so if we increase the amount of NO, then the forward reaction will go forward. Okay. Now, oops, yeah. So the next part will be for pressure changes. Now this, much like in the first unit when we talked about how to affect reaction rates, pressure changes only affect the gaseous particles. And again, when we talked about it in the first unit, the pressure change is really just increasing the concentration. All right, so same reaction, because in this reaction everything is a gas, so pressure will affect everything. Now, when you're thinking about how pressure will affect it, ask yourself the following. Which side has more gaseous molecules? Okay, this side has the greater gas pressure. Okay, so for example, in this one, we have 3 gas molecules here. So the reactant side has more gas pressure. Okay, more gas pressure. So when you increase the pressure, so if pressure goes up, the system will want to move in such a way as to reduce the pressure. So the system wants to reduce the pressure. So system will reduce pressure. Okay, and in order to do that for this particular reaction, the forward has to occur more. Forward reaction favored. Okay, and this kind of makes sense because if you think about it, if you increase the pressure in a system, you're going to squeeze the gas particles closer together. And when you squeeze the gas particles closer together, they'll be more likely to collide. So the NO will be more likely to collide with the Cl2 and therefore create this NOCl. Okay. Now, both sides will get affected by the pressure, but because there's more gas particles on the reactant side, the pressure will affect the reactant side a little bit more than it'll affect the product side. So it'll squeeze these 3 gas particles closer together, so they're more likely to react. And at the same time, though, it does squeeze the 2 NOCl particles together so they can react, but simply because there are more gas particles on the reactant side, this side will react slightly more often than this side, so that's why the forward reaction will be favored. Now the same is true if you remove the pressure in this system, then the system will want to go to a state where it increases the pressure. And in order to increase pressure, it has to create more gas, so the reverse reaction will occur. Okay. So anyway, so again, so Le Chatelier's principle states that, yeah, so anytime you change a system, the system will do something to undo that change. Okay? It becomes basically deciding if I'm increasing one thing, system will try to get rid of it. Now, what about a catalyst? A catalyst, would this really add, or would this really affect the system's equilibrium? If you think about what a catalyst does, in the last unit we discussed that all a catalyst does is it makes the forward reaction and the reverse reaction occur more often. But does it really favor either the forward or the reverse reaction? Not really, because when we talked about the energy diagram, for an uncatalyzed reaction, so let's say here's an uncatalyzed reaction, the catalyzed reaction equally favors both. So the amount that the activation energy drops is equal for both the forward and the reverse. So a catalyst doesn't actually favor either forward or reverse reaction because it equally affects both. All a catalyst will do is make the system reach equilibrium faster, because the forward and reverse reactions are occurring faster in both cases, so it just reaches equilibrium faster. Okay, so a system will reach equilibrium faster. Okay, that's all a catalyst does. That's all a catalyst will do, is it'll cause the system to reach equilibrium faster. It won't affect the equilibrium, so it won't cause a forward reaction to occur more often than a reverse reaction. It's just, yeah, it just makes the system get to equilibrium in a much faster way. Okay. All right. Now, if you guys have any questions, you can come find me on Friday. Your assignment will be as follows. All right, good morning, good afternoon, good evening, class. So just in case you guys weren't fully clear on Le Chatelier's principle, at least as far as how it pertains to chemical reactions, here's a few more examples. Le Chatelier's principle. So remember I said from the lesson that Le Chatelier's principle, the system will always try to counteract whatever change you apply to it. So let's say we have a reaction that is as follows. I'm just going to use a generic reaction. So A plus B goes to C plus some energy, let's say 100 kilojoules. Okay, and usually what will happen with a problem that deals with equilibrium is that a couple of things will happen. So which reaction is favored in each of the following? Which reaction is favored in, oops, that's terrible, in the following? And here's how you can look at it. So let's say A. So more A is added. Okay. So what you want to think about it when you read the problem is think to yourself, okay, so what are we doing? In this first part, we're adding more A. So we are increasing this amount. Okay. Now, since we're increasing the amount of A, the reaction will want to get rid of it. So the reaction will want to get rid of that A. So in order to get rid of the A, the forward reaction has to increase. Okay. So if I add more A to the system, this will correspond to the forward reaction. Forward reaction favored. Sometimes we'll also say product side is favored. Okay. Or products are favored. Those mean effectively the same thing, because it just means your forward reaction is increasing. All right, let's erase a couple of things. All right, so that's what happens if I increase A. Now, let's see. Let's say in the next part, I do something and I remove B. Well, if I remove B, that means that I am losing some of this. Okay, so in order for the reaction will want to recreate B, so the reaction will go this way. Okay, and we can say then that the reverse is favored. Reverse favored. Or we can say reactants are favored. Okay. Now a third situation, I think I briefly mentioned this, and I'll highlight it some more, is what to do with energy. And energy, this one's a little more confusing, I found. So this is partly why I'm doing this. So let's say we raise the temperature. Okay, raise temperature. Now, I didn't explain this too much in the first example, but when you raise the temperature, you're effectively raising the concentration of energy. Okay, so that's how you can look at it. Just raise the energy amount. Now, because we're raising this amount, well, the reaction will want to go this way to use it up. So again, here, reverse is favored. Reverse or reactants. Okay. Now that's an exothermic reaction. We did that yesterday. Let's do what happens with an endothermic reaction. Okay, so let's do another example. So let's go D plus, let's say 100 kilojoules produces E plus F. Okay, and let's for simplicity's sake do this, or I guess something different. We'll give them states of matter this time. All right, so let's do the same thing. Let's raise the temperature. So here's an endothermic reaction. We're going to raise the temperature. Raising the temperature again, wherever the energy appears, find it, wherever the energy appears, and just say, okay, if I'm raising the temperature, my energy is going up. When energy goes up, I want to get rid of it. In order to get rid of the energy, my forward reaction needs to go forward. Now, from an endothermic standpoint, or an endothermic reaction perspective, this should make sense, because if you give the endothermic reaction more energy, it is more likely to react. And that's exactly what it's doing. If I raise the energy, the reaction will react. So forward is favored in this case. Forward is favored. Okay. Now let's suppose then that we have a gas now. Let's get rid of this. Let's just make it bigger. There we go. All right. So this is a gas. So let's say I raise my pressure. Raise pressure. Now, which side is going to be affected more? Now, when you raise pressure, what you're really doing is you are effectively raising the concentration of all the gas particles present. Okay, so when you raise pressure, you raise the concentration of all the gas particles present. In this case, we have two gas particles, their concentrations are being raised, so it makes sense then that the reverse reaction is going to be favored, sorry, or the reactants are going to be favored. Okay. All right. There we go. Okay. Now, if we lower the temperature, let's say I lower the temperature. Well, think of it the same way. Where's our energy? Energy is here, and we're lowering the temperature. So energy goes down. So this goes down. Now, in order to recreate that, I have to drive my reaction backwards. So this will be the reverse reaction will be favored there. Okay. All right. So those are a couple more examples, and as you can see, all I really do is I look at the situation and I find whatever's changing in my reaction, and I either put an up arrow or a down arrow. Okay. If it's an up arrow, the reaction will tend to move away from it. If it's a down arrow, then the reaction will move towards it. Okay? That's kind of how you can think about it. Whatever is increasing, the reaction will want to use it up. Whatever is decreasing, the reaction will want to recreate it. Okay? And that's just the natural tendency of a lot of chemical reactions. Okay? We should be able to see something similar to that tomorrow, or the next, next lab. Whenever we do our next lab, we'll see. You'll be able to see this manipulation of equilibrium right before your very eyes. All right. Until then, keep working on your assignments, and again, if you have any questions, come find me.